This is Noel Patansu. I have the privilege and honor to speak at ETHOS 2025. This is Smokeless Chimney, and we are going to discuss combustion automation. This is biomass, wood, and pellet. At Smokeless Chimney, we make systems to measure smoke and control fires. This would apply to 13 million wood stoves in the USA and about 1 billion people heat or cook with solid fuel, according to the World Health Organization. Looking ahead, air quality will be an issue, and wood stoves will need to be monitored and controlled for clean burning. If I'm doing indoor air quality, I'm looking at CO2, CO, PM2.5, and VOCs. Measuring any two of these is an improvement to any home. We are a leader in measuring smoke. We have 3 patents, and we've earned a grant from the Department of Energy to work with 3 scientists at Berkeley. It is a pleasure to work with very sharp people. Smoke is a problem. There are laws regarding the opacity of smoke emissions from stacks. The law mentions Method 28, but all you really have to remember is the Ringelmann method. It's a method from the 1890s from the Bureau of Mines, and it's colored pieces of paper. Our solution is to use an opacity monitor and combustion air control systems. We make combustion airflow systems and smoke measurement systems. These devices can be used together or individually. For example, the University of Berkeley, their National Fire Lab, they only want to use the smoke measurement system. I have one system that uses both. I also have another wood stove that uses only the combustion airflow system. They both work together. They both work apart. A brief history of smoke measurement. My first job in smoke measurement was in 1982. Got hired by a large fire lab that had about 6 to 10 pieces of equipment that required regular calibration of their smoke measurement systems. In 2005, incandescent light and photoresistors were still being used. When I presented to the Fire Materials Conference in 2018, we were using digital light sensors and photodiodes. There's a big difference between the two. Now I'm using multi-band digital light sensors and white LEDs. I can use narrow band LEDs, but I like the broad spectrum white LEDs, and you'll see why. I'm not using lasers or coherent light. This is a chart of smoke measurement. It is done on our system that controls the airflow and measures the smoke. This is only opacity. Now there's about 2 hours of data here, and it collects data every 5 seconds. What we can see is that the red line is 20%. That's the point where you don't want to exceed that for more than 6 minutes consecutively in any hour. So we have a startup time about 4 minutes over the 20%, and that's allowed because it's part of the startup time. We have 2 other events that briefly go over the line, but just for a few seconds. We'll say a minute each. For the most part, we're running around 10, and then after we stop putting fuel on, we're running around 5% opacity. To proceed further, we're going to have to give a briefing on principles of light scatter. Raylan scattering is up in the upper atmosphere where molecules are not very close together. The blue light is scattered, and that gives us our blue sky. Closer to the Earth, let's say within a mile of the ground, the molecules are too close together, so we're under my scattering rules and Tyndall scattering rules. My scattering is when particles are larger than the peak wavelength, it blocks the light, resulting in opacity. So opacity is under the my scattering rules. Tyndall scatter occurs in colloids like smoke when particles are smaller than the peak wavelength. It preferentially scatters the blue light. And when we look at the data from the sensor, we can decide whether we're under Tyndall scattering rules or it's just simply blue scatter. Working with light scatter, I needed to make one slide to clarify that we've come up with a new term called color shift. It is the normalized change in peak wavelength. This is the same chart that's been rescaled, and we include our color shift value. These items plot well together and are in the same magnitude range. What I see is that opacity gives us a certain amount of information, but when we overlay the color shift on top of it, we see a lot more detail in what's happening in the wood stove. For example, at 0.5 hours, we've got fairly low opacity, but we have what appears to be a large number of fine particles leaving our chimney that you can't see. The color shift is in nanometers in shift in the peak wavelength. In other words, we're saying the color of the light is shifted to the red just a little bit. 100 nanometers, 120 nanometers on the peaks on this one. We're going to talk about combustion control. Design parameters are safety first, efficiency, and emissions. When you get the efficiency right, the emissions just come in line. We're going to adjust our airflow, the mass flow rate, and the airflow pattern. For our wood burning phases, we're going to talk about new fuel insertion, endothermic phase, peak heat phase, and embers, or the tail of the fire. I'm going to talk about waveforms, and I think everybody can understand the sine wave and understands that a violin sounds different than a piano. Well, I kind of used the waveform for a piano to help me get started. This is a 1-minute section of data from a wood stove that's been running for about 50 minutes. And you can see 8 little sections of the waveform. These are the commands sent to the fan, where it spins up, spins down, spins up, spins down, and the fan takes time to spin up and spin down. However, these are the commands sent to the fan. And the result is over 1 minute, we get about a 6-degree rise in our wood stove from 401 to 406 in 1 minute. That's a great rate of rise. So this airflow pattern is working. This is a chart I made to explain to people what this waveform looks like. About the first half a second, it's getting the fan spinning. And then depending on the duty cycle that I send to the fan, it follows a very described curve for about 8 seconds. Now, if it's spinning really fast, it's going to go beyond 8 seconds, but then the next waveform takes over. This is a photo of the alpha unit. It's been rebuilt several times. 2 units are down at University of Berkeley. They look a little better. I'm going to design it without the windows for my gangly wires. On the right is a light source. This one is made of transparent or translucent PETG, and it leaks a lot of light out to the side. I tried different materials, but that's essentially what the light source looks like. This is a chart of the normalized light channels. We have infrared in dark red. We have blue, green, red, and clear. Over 8 hours, there's about 5,900 data points on each line. There's a huge amount of information in this chart. One of the scientists I'm working with thinks all the data that we need is in this batch of information here. He thinks the raw numbers coming off the sensor, he can get everything he needs off that. But let me tell you what I see. So we get into the test about an hour and the infrared goes above 100%. I'm saying that's heat from the chimney, hot particles from the chimney radiating into the sensor. The other thing to look for is the blue caps on the stalactites. So if you know stalactites, they hold tight to the ceiling. The stalagmites might have. So these stalactites have blue caps. That means the blue scattered more than the other wavelengths of light. That's the shift to the red that you see in the color shift. A brief look at what the control box display looks like and what the fans look like. These fans spin up to around 3,000 RPM and create approximately 0.3 of an inch of water column. These are the takeaways from this Safety first. We want our wood stoves, our pellet stoves to be safe. Every wood stove is unique, has a unique operator, chimney system, and house. Fire control with small air adjustments or patterns are key. There are 13 million wood and pellet stoves in the USA alone, and 1 billion people heat or cook with biomass. I am Noel Patonsu. I am Smokeless Chimney. You can find me on YouTube, Reddit, Facebook, and Blue Sky.